I don't have your exams graded yet. It's gonna take a little while.
Just to like calm me down, you did like get the email.
I did,
about that?
yes, sorry, I did not, yes, I did get your email, yes, absolutely. You don't happen to have the original, do you?
It was all on whiteboard, and I just erased after each time and I took a photo.
Oh, okay, you, Alan did something kind of similar. Okay, cool. All right, friends, let's see here. So new web work, we'll start on this today. I think I sent out an email earlier today, right? Like bring your laptops. Okay. Cool. It's not open yet, so don't try to do it yet. I want to talk about it anyway. It'll make it a lot easier. That'll be due on Sunday, so we have time on Friday to talk about it a little bit and so forth. There's a couple special facts that I want to talk about we're going to need today. So this is the first one. Let's let R just be a constant number. So it's just, it's a number, it's fixed, it's not a variable. Let's kind of think about this for a second, because I want to think about what happens to powers of that number. So let's say I have like 1/2 and I was raising that to the nth power. This is a really important thing to understand, and once you understand it, you'll be able to see some things really quickly. So let's think about what this is. I don't know why I'm writing in this lower left corner here. I guess it's so Alan has to, like, I don't know, stand up or something, but hopefully you can kind of see it a little bit. No, you're good. Okay, cool. So when n is 1, that's 1/2. When n is 2, it's 1/2 squared. When n is 3, it's 1/8. When n is 4, it's 1/16. And it's just getting smaller and smaller. Where do you think it's headed? Like if as n gets larger and larger, what do you think this quantity is headed toward? 0, absolutely. So let's do a different one here. If I have n here, and then I have 2 to the n, what is that thing doing? What's that one doing? Going to infinity, yeah? Just keeps blowing up. And so I just wanted to make what I'm about to write seem plausible to you, that this has a couple possibilities. And then there's one I didn't mention. But let's say here that if R is, and this might be, actually, so the limit is 0 if R is between -1 and 1. So this could have been a -1/2 here as well. And how would that have changed things? This could have been a negative, then this would be positive, and this would be negative, and this would be positive. But if you looked at the sequence the way I was recommending last time, you can see it getting closer and closer to 0 as we move out. Even though it's oscillating, it's dying out as we head toward infinity with that exponent. So this is a really important factor, that limit will be 0 no matter what. So for example, if I asked you, what is the limit of -7/8 n as n goes to infinity, you just go, well, that number is less than 1 in magnitude. Realize this just means this, right? That the magnitude of R is less than 1, so that's just a 0. Nothing crazy. But if I had this, limit as n goes to infinity of -8/7, now I've got a number bigger than 1 in magnitude. It's going to do something like this, but it's just going to flip back and forth. This is going to diverge. Because what's going to happen with this one is you're going to see, let's see, so there should be an n there, excuse me. You're going to be -8/7, then 64/49, then negative whatever the hell 8 cubed and 7 cubed is. And then this. So we're going to see this kind of behavior. We're definitely not settling down. We are diverging. So this is where, instead of just saying, like over here, when I asked what happened with this one, Isaac said, oh, this goes to infinity. Absolutely right. Just keeps getting bigger and bigger. That's a kind of diverging. It means we're not settling down to a nice finite value, but you can diverge in a couple different ways. And so what I want to say here is that this diverges if R is bigger than 1 in magnitude. So realize this means two things. This means either R is less than -1 or r is bigger than positive 1. And then what if r is 1?
Just goes to 1, right?
It just stays at 1, yeah. So it's equal to 1 if r equals 1. Really important fact for what we're going to do today. Simple, all you really need to take away from it is this, but I hope you understand it too. That's really the important part. So before we get into talking about the ancient Greek philosopher Zeno, which is like one of my favorite stories, I want to just put a couple of rules up here first. So last time we talked about sequences. So a sequence, like this, quick review, is a list of numbers. If I write this, or sometimes this, notice how there's no list of n. There's an implied range here. So there's an implied range for n. And usually it's n equals 1, 2, 3, on up. Sometimes people write that, but rarely do they do that. So when I see this, or this, what I think of is a list. This just represents a list, and it's a sub 1, a sub 2, a sub 3. We may have a formula for each one of those, we may not. So here's a case where I do have an example. If I write this, n minus 1 over n, and I say here's a sequence, it might help to say where n starts. So kind of like with integrals, you could do that if you wanted. Here's the starting index, here's the ending index, and that means we don't ever end. But what this just means is plug in n equals 1, plug in n equals 2 to get the list. So this is when n equals 1, 0 over 1. When n equals 2, it's 1/2, 2/3, 3/4, 4/5, on down the way. There's a couple little details I didn't really get to talk about. What is this? What is the limit as n goes to infinity of this sequence? Where's that headed? You kind of look at the list and make a how many fingers? Where's that thing going? I've seen one finger. I've seen 2 fingers. So why do you say that, Gabe?
Because it's less than 1.
Oh, so now be careful here. This is not that over there. So I'm really glad you said that. And I see where you're coming at with that. So over here, this is a fixed thing to a power. So that's like I've got, like pi to the n or something. Notice here the exponent is the thing that's moving. But over here, there's no exponent.
Okay.
So I like that you were like trying to tie it back into that. Yeah, so I'm seeing 2. Yeah, I'm seeing another correct finger. Okay, I'm seeing, all right. Oh, if we just each hold up 1 finger, we've actually got it right. Because the limit is 1. Why is that? Well, notice here that the top and bottom are getting closer relative to their size, but we could see this a couple of ways. This is an infinity over an infinity form. So I could L'Hopital it, and by L'Hopital, this limit is derivative of the top over the derivative of the bottom. Hey, that's sweet. 1, always 1. Another way you could see this, and I just want to talk about this, is you could rewrite it. This is n over n minus 1 over n. And I just do a little algebra, so that's the limit of 1 minus 1 over n, and we've seen this a billion times. Something fixed over something blowing up. This piece goes to 0, so that piece goes to 0 there, Gabe. But I still got the 1. So, let's say I've got some sequences. So I've got a sub n, I'll come back to Zeno in a minute, that was for my sake. A sub n and b sub n are sequences, so assume that. They're lists of numbers. Also assume that they settle down to something. And the limit of a sub n is a. It's some number, it settles down to some a. So what do I mean by that? Here's n, here's a sub n, and here's the number a. What it means is that if I move out far enough, I can get as close to that number as you want. It may bounce around it, but way out here, so in other words for this, for large n, a sub n is pretty much close to the number a. That's what it means to say that statement. And then we have the limit b sub n is b. So if I know those two limits exist, then I have these properties. They're just simple. We're gonna put them up here and then use them when we need them. But if I take the limit of the sum of those, and I'll show you what I mean in just a second, that's the sum of the limits. So one neat way to say this is limit of the sum is sum of the limits. So we got that. So that's property one. Property two is I could put a minus in there, and I'm going to make that part of this. So I could put a minus in there, and then that minus translates over to there. So limit of sum, or difference, is the difference of the limits. If I have the limit of the product, so this is getting kind of hectic up here, but if I have the limit of a sub n times b sub n, that's just a times b. And then one last one, limit of a sub n over b sub n equals a over b, as long as that b's not 0, because that would be bad. So provided b is not equal to 0. So those are just neat ways of combining sequences, or combining sequences that we might need along the way. I guess I should actually ask really quick here, are there any questions on that current web work that's out, the one on sequences? It's pretty straightforward, I think. Everybody, all right. I'm gonna take your word on it. Sounds good. Okay. So we are starting to depart. So sequences are lists. And I want to get this clear because this is some terminology lots of folks have had trouble with over the years. Sequences equal lists. Series equals sums. A lot of times people confuse those two terms. We're about to move into sums. That's our next study here. So we are moving into infinite series. You have to understand sequences just a little before you can do this right, though. So back in ancient Greece, there was a philosopher, Zeno, and he wrote, anybody ever read any Zeno arguments in like a philosophy class, high school or anything like that? He had all these crazy arguments, like he tried to prove motion was impossible in a couple of different ways. And one of the ways was with the following experiment. So Zeno says, distance from me to that wall is 1 unit. That's the distance I want to travel. Call that 1. Before I can get to that door, I have to travel half of it. So I've traveled half. I write down a 1/2 on the board. Now I still have to travel half the remaining distance, so that's a quarter. So I've traveled a half plus a quarter. Still have to travel half the distance to get to the wall, so I travel 1/8. Now I'm a half plus a quarter plus 1/8. Wherever that gets me, I don't know how many eighths that is, but getting closer. Then I have to travel half that distance, and then half that distance. And I never make it there because there's always half the distance remaining to travel. Now, that's bullshit, obviously. But it's an interesting experiment. And the question is, what is going wrong? Why does that sound all right, but not make sense in reality? So let's look at what Zeno was saying. He's saying that to travel 1 unit, let me write this up here. So let's call that 1. I first have to travel a half. So 1/2. And then I have to travel half of that, so that's a half plus a quarter. And travel half of the remaining distance there, that's an eighth, plus a 16th, plus a 32nd, and my God, this never ends. Why do I get to the wall? Well, there's a couple weird things going on here. One is that the rate of travel is changing and all sorts of stuff like that. But it's just a weird construct of the mind that makes this seem like it couldn't work. But this back when, this is pretty cool thinking, pretty cool thought experiment. But what I want to prove to you today and have you believe completely is that this actually does add up to something. It adds up to a 1. So this is a weird idea. This is like only mathematicians think like this. This is like one of the reasons I love math. Because we're going to be able to grasp infinity in a way. This is this process that never goes on. There's a thing in mathematics that you may or may not have ever heard about, but it's called the axiom of choice. And this is something only a mathematician would care about. It's basically an axiom. So an axiom means something I assume that doesn't necessarily have a precursor in logic. So this is like some root of everything that comes after it. So the axiom of choice says, if I have infinitely many boxes or infinitely many choices, I can do each of those choices. So if I gave you infinitely many boxes to fill with infinitely many balls, axiom of choice says, yeah, sure, you could do that. In reality, we never would have enough time. You would never have enough time to do any infinite task in your short little lifetime, or any if you'd start at the beginning of humanity, whenever you think that is, if it's like when you think the first Anthropithecus started walking around on the ground, or if you think it's some other thing. So it's still not that much time. It's not an infinite amount of time. So to think about that is crazy. Some mathematicians have rejected that and said that sounds like bullshit. The good news is it doesn't matter. The great news is math lives if this is true or if this is false. There's a couple mathy things like that people have proven, hey, math is okay with this and math is okay without this. And this is such a thing. An axiom of choice. Don't worry, we're not going to dig much deeper into that, even though I would love to. I want to get to the heart of this. So this is an infinite sum right here. So this is an infinite sum, and the fancy word for that is infinite series. This is the rest of the semester for us, understanding these infinite sums and being able to work with them. And we're going to start off with the easiest to handle kind. This one that Zeno modeled for us thousands of years ago. We're going to start right here, and we're going to take it way further than Zeno did. The stuff that we're doing is just like a couple hundred years old. So like all this stuff, most of the math you've ever studied is in the last couple hundred years, and most of it is literally like 200 years ago, not like last week. So let's look at this series here. It's got a very particular form. So this series has a unique form. And the form goes like this. I've got some number r. And here r is a half. Looks like I'm starting with a half. And then I multiply, start off with a. You can change your r into an a. So I've got this first term. And then I multiply by some number to get to the next one. So I'm going to multiply by r, so I'm going to write times r there, and add on a times r. So here, a equals 1/2, and I multiply by 1/2 to get to the next term. Each of these is called the term. So the terms are the things you're adding together. So notice that to get from one term to the next, I always multiply by 1/2. So I've got this constant ratio between the terms. And that's what I want to indicate here. I start somewhere. To get to the next term, I multiply by r. To get to the next term, I multiply by r again. And so on and so forth. So times r, and ar cubed, and we're just going to let that roll out like that. Keep on doing that. So the next little exploration is, when does this make sense? And by makes sense, I mean add up to a finite value. That's what I mean by makes sense. When can we actually say this adds up to something? Like we want to say this adds up to 1. So here's a little game we're going to take a look at. First thing we're going to look at is a construct that we'll look at a number of times. This is going to equal the nth partial sum. Now what does that mean? That just means the sum of the first n terms. In the series. So you kind of like, you're truncating your series. You're cutting off the ellipses at the end, and you're saying, oh, this stops after I do n things added together. So for this series, it's going to be a, that's my first term. AR is my second term. AR squared is my third term. So now look at the rhythm. The exponent on the r is 1 less than the term number. This is first term, second term, third term, fourth term. So the nth term would have n minus 1 as its exponent. Check that out for a second. I'm going to rewrite that. Let me know if that makes sense, because this stuff starts to get like kind of weird. It's definitely new, so let me know if anything needs clarification. One of my favorite tricks in math is next. I'm going to take this thing and multiply it by r, just a number. So I'm going to multiply it by r and write it underneath. And let's organize things here. And let's think about what's about to happen. So this will become AR, this will become AR squared, AR cubed, AR to the fourth. This will become AR to the nth. Let's line stuff up. So A times R is AR. So everything kind of shifts up a power, plus AR squared plus AR cubed. The AR cubed came from this one. And then this one here would still be in there. This came from ARn minus 2. The one right before this one now becomes that one. And then this one here, when I multiply by r, becomes AR to the nth. Draw a line underneath those. And maybe you see some. What do you see, Isaac?
It looks like there's a bit of a contradiction of sorts in there. Like it looks like a little bit of silliness is happening.
Ooh,
But
like how?
I'm not
Explain.
I don't feel like I'm qualified enough to say how, but
I appreciate your
definitely thought it
discomfort.
was up.
So Isaac's feeling uncomfortable with this. And that's good. Like if you're not feeling uncomfortable about this stuff, you're probably checked out. So that's good. Yes, ma'am.
It looks like you just took the first term and tacked it onto the end and made it a, like...
It does look like that, right?
Yeah.
Yeah, totally. So I think this multiply this thing by r, it kind of looks like the end of it with an extra term tacked on, right? There's a lot of similarities. So I think what Sophie's getting at and what Isaac is getting at is that there's a lot of stuff that looks the same.
Looks like you can just keep pushing it over and over forever by multiplying r.
Absolutely, could keep on cranking it over to the right. Yeah, absolutely. If I did r squared, it would move it a little bit more and shift it. But I'm going to stop here and subtract, because stuff will cancel. So on the left side, what do we get? We get the original sum of the first n terms minus r times s sub n. So just take those down, equals, what do I have on the right?
A of r to the n.
A minus AR to the n, because all this stuff cancels, right? And don't forget, you're subtracting, so that becomes negative, and that stays positive. So I'm going to do a little bit more work here. I see some nice things that can be factored here. You could pull the S sub n out. And over here, you can pull the A out. But look, friends, I can now solve for S sub n. So if I just divide both sides by 1 minus r, I get S sub n is first term times 1 minus r to the nth over 1 minus r. That's a formula that tells me exactly how to get the sum of this first thing, the nth partial sum, just in a nice slick way. Let me give you an example of how to use this in a cool way. So we can definitely use that to do something like this. We'll come back to Zeno in a minute because we're not up to infinity yet. We're just getting there. So what if I took 2/3 minus 4/9 plus 8/27 minus plus, and I went all the way up. So do you see what is the common ratio here? What am I multiplying by to get from one to the next? What do you? Negative 2/3, right? So check that out, there's a sign change. So here the common ratio is negative 2/3. Same thing here. So, gosh, I should have, this is kind of painful, but I'm gonna cheese out and I'm gonna say we did this, let's see, that's first, second, third. I went all the way up to negative 2/3 to the, let's see, that's cubed, so let's just say 6th power, whatever the hell that is. I don't know. 2 to the 6th is 64. I don't know what 3 to the 6th is. And it doesn't matter. It don't matter. So, if I said to you, hey, find that sum for me right now, you would have to go in and crank out all these intermediate terms and then get your calculator out and go 0.66 minus whatever the hell that is plus blah, blah, blah. Don't need that. I can go to that formula. So, how many terms do I have here? Remember, n equals the number of terms. Right? Because here we're starting counting at 0, 1, 2, 3, on up to n minus 1. That's n things. N equals the number of terms in your sum. R is the common ratio. A is the first term. And so I can just bless you.
Thank you.
So I'll just come over here and say, using my formula, with n equals 1, what do we got here? 6? Does that sound right? 6 things? Because this is 2, whoa.
7, right?
6 and 0. Yes, and this should be negative. If that's, this should be, change these up. I got the signs wrong. If it's negative 2/3, then this needs to be plus minus plus minus. Plus minus. So what was it?
Should it be 7 because we started at 0?
Let's see. Over there I did, but I didn't. Oh, I see what you're saying. Let's see. So this is negative 2/3 to the first, right? This is negative 2/3 to the second. So notice that the exponent on this one actually does sync up to the number of terms. Does that make sense? Okay, cool. I'm glad you're like keeping with this. So we got r equals that, n equals this. And a is the first term, it's negative 2/3. So the sum is equal to, go to your formula. It's going to be a, which is negative 2/3, times 1 minus the common ratio, negative 2/3 to the number of terms. I still have to figure that shit out apparently. Over 1 minus the common ratio. Now it takes fewer calculator clicks. I guess. It's still gonna take a little bit of work. Let's do it. I'm just kind of curious. I might need a calculator friend, for sure. So let's see, so we got negative 2/3 times 1 minus, I need this negative 2/3 to the 6th. And I think it's gonna be 64, but what is 3 to the 6th? I guess that's what I really need. Could somebody do that for me, or do I have to do it myself? Don't make me do it myself. 3 squared, 3 squared, 3 squared. 9, okay, well, you're too late. Go, did it myself. Damn it. And then the bottom becomes a plus, so that's 1 plus 2/3, that's 5/3. And then I could simplify a little bit here. This is gonna be, let's see, 3/5 times that. And then 1 minus 729/9 is 729 minus 64. Could somebody do this one for me, please? 729 minus 64. I think I actually, maybe it's
665.
665, that sounds great, thank you. So 665 over 729. And then some simple stuff is gonna cancel here. Notice the answer is gonna be negative. So I'm gonna get negative 2/5 times 665, 729ths. I have no freaking clue what that is. And I kinda don't care. It's the answer. We're almost right there. So equals the sum. Still probably beats going through and doing all that shit. And imagine if I had done this to us. Right? So now you see where it might be useful. If I said, add up the first 60 terms, you'd be like, oh, fuck this, I quit. I'm not doing this class. I got an A. I'm almost done. I'm not doing that. That's it. Take me out. I withdraw. I hope you don't do that. You might have some other issues if you're making decisions like that. But, look at the sum. Let's come back up and summarize what I've got so far. So this formula here that we have for this series, I'm gonna put it up here. That sum adds up to A times 1 minus R to the nth over 1 minus R. Cool. So that's where we're at. And now, if we want to let this thing go to infinity, we're just going to take the limit as n goes to infinity. So in other words, so let me write that out. Now let n go to infinity. And the left-hand side becomes an infinite sum. That n goes away. It just keeps on cruising. The right side becomes this limit. And there's only one piece moving in there, and it's that sucker right there. So this is the limit as n goes to infinity of a times 1 minus, oh, excuse me, put the limit inside there. So this is a times 1 minus this limit, which you actually saw a little earlier today. Right? Yeah, we had a little thing on the board, becoming German, strangely. It's like the second time this week. Become Deutsch. What does this do? So it's a limit as n goes to infinity of a constant, and the exponent keeps getting bigger and bigger. We had a couple possibilities, right? What happened if r was less than 1 in magnitude? Where did that limit go? 0. Beautiful. So if r is a fraction, even a negative fraction, like between -1 and 1, that dies. If r equals 1, well, r equals 1 sounds bad because I'm dividing by 0. So r equals 1, das ist verboten. The transformation is complete. because we division by 0 there, right? And then if r is bigger than 1, this diverges. So if r, let's just say this, if r is greater than or equal to 1, it diverges. So this thing, if the magnitude of r is less than 1, we're almost done. We almost got a beautiful freaking formula. If the magnitude of r is less than 1, this is equal to a times 1 minus 0 over 1 minus r. And that's how you add up an infinite list. Yes, Isaac.
I know it's probably not what you're like the direction you're hoping to take
Oh,
this
I
section,
don't
so I'll
know.
keep it brief. But like, I don't know. I feel like infinite series are some of the most like unintuitive parts of like math up until like that which I've learned so far. And so I can't like understand why like if r is equal to 1, like not within the context of like the formula that you got from like
Yes.
working through the series, but like just within the series itself, why would that not be allowed?
All right, let's
That-
take a look.
that-
Awesome
It looks fine to
question.
me, right?
I love that question. That's a beautiful question. So let's rewrite the series. Let's write this one with r equals 1. What does it look like?
It's just a plus a plus a. Why is that not allowed?
Infinitely many times. Let's say a is not 0. If a is 0, this isn't very interesting at all, right? This is just 0. If a is not 0, let's say give me a small number.
0.5.
0.5. What is, if I keep adding 0.5 to itself, does it settle down?
No.
So would that sum settle down?
No.
That sum would blow up to infinity.
So it diverges.
It diverges.
But it doesn't do anything like weird, which was implied by like if r was equal to 1. Like
Yeah, it diverges definitely. But I did kind of say that here in the summary.
is that a greater than or equal to?
That is a greater than or equal to,
Oh,
yes.
okay, yes.
You feel good about that?
Yes.
An
I didn't know
awesome
if there was like
question.
some like weird like thing that like emerged once you like tried to like make a solution for this. I don't know. Because that seems pretty typical of like math.
It does. It's so math. Yeah, absolutely. But that makes you feel better about the r equals 1 case?
Yes.
Okay, 1 over 1. Cool. So, Zeno, wake up, bro. I want to show you something. I got to the door. That was Zeno's sum. What's the common ratio? R. Half. So first thing you have to identify, and this is going to become a skill that you need to learn, is identifying the kind of sum that we have. We're going to have different ones. This is the most elementary. This is called a geometric sum because there's a common ratio between terms. That just means that if you know one term, you automatically know the next because it's the same multiplication factor as the previous ones. So here r equals a half. My first term is 1/2. And then I check to myself, is r less than 1 in magnitude? Yeah. Is a half less than 1? Shit, I hope we can answer that question. Yeah. Yes. So I can use the formula. And I get that this sum, so this converges, the series converges, that means it adds up to something finite, to a over 1 minus r, which is 1/2, the first term, minus 1 minus the common ratio, that's 1/2 over 1/2, that's freaking 1. In your face, Zeno. Hopefully there's no ghost of Zeno floating about. Like you're knocking, clawing at my door tonight. Like the monkey's paw. Zeno's paw. Let me show you something else that's kind of cool because of this. So I've seen some pretty funky, I've seen a lot of pretty bad math on YouTube. do a lot of really good math too. But there's some bullshit math going around with this number omega that people have done weird stuff with. And it kind of falls back onto this. So, you know, if you had a decimal representation of a number. So actually, first off, let's start with this. What number is that? If I just say repeating forever and ever.
A third?
We say that's a third, right? And you type that in your calculator and you get like however many decimals of precision onto it. And we're just taught that that's a third because that's what a calculator gives us. But let's prove it's a third. So this is 3/10 plus 3 100ths plus 3 1,000ths plus 3 10,000ths, on and on and on, right? That's what that means. It's just decimal places. So this is 3 over 10 plus 3 over 10 squared, 3 over 10 cubed, 3 over 10 to the 4th, and forever and ever. It's an infinite sum. When I write that number, it's an infinite sum. It's a geometric series, in fact. What is the common ratio? What do you multiply from to get from term to term? Multiply by 1/10. Make sure you see that. Looks like 16. Should be 10. What's the first term? 3/10. Can you add that up for me using the formula, please, my friends? Can you prove, since r is less than 1 in magnitude, we're solid, we can proceed, what does the formula tell us that adds up to? This isn't the bullshit math. I'll show you the bullshit math in just a second. Hopefully you're getting a third. I mean, you should expect it because we were just talking about a third and stuff, right? But look at the formula providing that proof and a feeling of solidity to that claim. So here's the number I'm thinking about. I actually, I've been in a battle on Reddit with some person who doesn't quite know what they're talking about over this number. He's getting a lot of downvotes, so nobody agrees with this guy. It's in like some math forum or something like that. But everybody's dumping on this guy. And he's just dug in. He's just fucking dug in on this debate. What does that add up to? Can you tell me? What do you say? What do you think it adds up to, Isaac?
1.
We hear a 1? Seems like a 1, right? Feels like a 1, but it also feels wrong. Boy.
Well, if we look at the other number, couldn't we just say it's 3 times that?
That's good. That's a great argument. So check it out. Gwen's like, wait, that's 3 times that number. Right? It is. So it's 3 times the third. So it is 1. So that, I love that. That's like a quick way to rely on the stuff we've already done to just note that, oh, this is 3 times that, so this equals 3 times a third. You could also prove to yourself using this formula. What would change here?
It'll be
A. Just the first term, right? It would just be a 9/10 up here as your first term, and then you're still multiplying by a 10th to get to the next decimal place. So there's a couple of ways to see it, but one of the amazing things in our number system is this. And some people don't understand, numbers don't have unique representations. The way we write numbers with our decimal system is not unique. So that's kind of an incredible fact. There are, let me just write that out in a sentence. So decimal representations are are not unique. Because I can take the number 2 and write it like this, get the same thing. You can take any number and do that to it. There's no one way to write any particular decimal number using this representational system. All right, let's do a few problems together. I think it's time. And we definitely got time. I want to do at least a couple examples before I set you loose on that web work. What if I gave you, ooh, here's a fun problem, and it's kind of web worky. What if I gave you this sum, 1/2 minus 3, let's do a couple problems, 9/8 minus plus. So my first question to you is, what kind of a series is that? Well, you clearly haven't been here if you don't know the answer to that. You've been checked out. What kind of a series? What kind of series are we talking about today? Geometric. That's a freaking geometric series. What is the common ratio? Does it converge? You wouldn't know it was geometric on another day. You would have to test that. Geometric with R equals what? What do you think, Isaac?
Is it -3/2?
-3/2, yeah. And you just need to look at the first two. What do you multiply to get from the top across? That's a -3. When you get down to the bottom, -3/2. Does that make sense to everybody? Does that series converge? Does that add up to a finite value? Why not?
Because it's the absolute value of it is greater than 1.
Because R is bigger than 1 in magnitude. Yep, beautiful. So this series diverges since magnitude of R is equal to 3/2, which is bigger than 1. So it's all about being less than 1 in magnitude. Let me give you one little challenge problem here. This is kind of a fun thing. Remember good old repeated decimals? You remember when you learned that in grade school and you saw someone put the bar over and they felt really cool because they knew it, maybe you didn't. I remember this moment when someone showed me that and I was like, oh, really? So this actually represents this thing here. So I guess my question to you is, can you write that as a fraction for me using the things we've talked about today? So step 1 is write that as a geometric series. Use the series formula, because that is a number. It converges. In fact, it converges to that number, so we don't need to worry about that. What is A, what is R, and what is the sum of that number? I'm going to run to the restroom real quick, because that's what I do at this time of day. And every time I always say it, too. So, we're going to freaking live. 135 over 1,000 for that first one. Plus 135 over a 1 with 6 zeros behind. That's 10 cubed. That's 10 to the 6th. That might get you rolling. Yeah, that's it. Nice. Anybody else got some? The 900, I don't, it's close, but it's not exactly. Wait, is it 900? Close. Oh, so the ratio isn't 1/10. That's the problem. The ratio is 1/1,000. Actually, there you go. That's the problem. But, and also, William, I would just go right to that final formula as opposed to worrying about that limit. You know, just go to this one right away. Yeah, yeah. It's not a problem. Abraham, did you get some? What you got? That'd be it. Yeah. Yeah. Wait, where's your sum? So.
Oh.
So we're looking for some. So, okay, so I agree with that, but your common ratio isn't 1/10 because, check it out here, Gabe. To go from the 135 over 10 cubed, which is the 135, that you have to go by 10 you have to 10 cubed, 1 over 10 cubed, sorry.
Okay, that makes sense.
Does that make sense? Yeah. Let's check this out together. So it's a leap, and if you don't see this, it really makes it challenging. There's a lot of things to see here before we can get to the heart of it. But that's my first term. My common ratio is 1 over 10 cubed. So I'm multiplying by 1,000 every time. That times 1,000 is that, times 1,000 is that. So R is 1 over 1,000. And so my sum, and so R is less than 1, yay. Better be, otherwise I can't write numbers. And the sum is going to be 135 over 1,000 over 1 minus 1,000. So that's 135 over 1,000. And actually, ooh, you could just take the top and bottom and multiply them by 1,000. Multiply the top by 1,000. Multiply the bottom by 1,000. You get 1,000 minus 1. And no matter how you get there, 135 over 999 is your answer. Can this be simplified? This fraction?
5 over 37.
What'd you get?
5 over 37.
Ooh, that's pretty good. How'd you get that, Abraham? That's
I
pretty
just kept dividing both sides by 3.
That's
Right
nice.
there.
That's really nice. So, just if someone were to ever ask you, let's talk, this isn't calculus. How do I know the top number is divisible by 3? Oh, calculator would do it. Yeah, let's say, okay, no, post-apocalypse.
If we add all the numbers that, how do you say?
Yeah, you added
What were you gonna say, Jake?
you just add up the numbers, and then if that number is divisible by 3.
There you go. Yeah, that's what you were saying, right, Voin? Yeah. So add up all the digits. If that number is divisible by 3, the number itself is divisible by 3. So check this out. These add up to 9. That's divisible by 3. So I can pull a factor of 3 out. Abraham did that a bunch of times for us. This one sure the hell is divisible by 3. You add up the digits, you get 27. You might say to yourself, is 27 divisible by 3? Well, add the digits. You get 9. Yep. So you can just kind of keep on like distilling things down that way. So this could be simpler. Abraham, what was that you got, sir?
The final one I got was 5/37.
That's pretty. That's cool. Neat. How about this? How about we call it a day? Does this sound okay? Anybody upset with that? And then on Friday, come on in and we'll work on the web work together. Let's do that. Good to see you today, Isaac. Been a long time.
I had a good reason.
Did you? You okay?
Yeah.
Okay, good. Okay. Thank you. Thank you. Thanks. Bye-bye.
You want to stop?
Please.